In this problem, we are thinking about light that's incident on a double slit and creating an interference pattern on a screen that's far away. And we want to know about the first order maxima. So let me walk you through the diagram first, and then we can get to where the first order maxima is. So in this picture, we have these lines here. They represent the incoming light wave. So the big idea here is that light behaves like a wave. That means it has a wavelength. So we have the wavelength indicated here. And this wave is incident on two openings. So if it was a stream of particles hitting two openings, then some of the particles would go through this one, some would go through this one, and you'd end up on the screen over here with two dots. However, light behaves like a wave, so that means each of these openings becomes a source of a new wave, and waves will spread out from those openings. So they don't go straight through, instead they treat this opening like a new source of waves, and they emanate out like this. Okay, sort of spreading out as they go. That means the wave from this one can interfere with the wave from this one, and you can get an interference pattern on the screen over here. The important numbers in this problem are the spacing between the two slits, which is d. Okay, so that's the distance from here to here. And how far away the screen is, L. All right, we also need to know what the wavelength of the light is, and so we have all of that information right here. The wavelength is 633 nanometers, the slit spacing is 0.4 millimeters, and the screen is 2 meters away. The thing that determines whether or not you get a light spot, a bright spot, or a dark spot is the path difference, the difference in length that the light has to travel to get there. Okay, so they start out in phase, but once they get to the two openings, now they're out of phase. And they're out of phase because there's a slight difference in the distance that they have to travel to get where they're going. This right here represents that path difference. So delta represents the path difference, and it's equal to, by geometry, d times the sine of the angle. So if we look off at some angle, then this distance times the sine of the angle gives me how much difference there is in the paths between these two beams. So for example, if the angle is 30 degrees, then the path difference would be 0.4 millimeters, the d, times the sine of 30, which is a half. So we get 0.2 millimeters, meaning if you look off in a direction that's 30 degrees, then the light traveling from this one will have to go about 0.2 millimeters further than the light from this one. So if you originally had crest and crest together and you separate them by 0.2 millimeters, now there's a path difference, and it could be either constructive interference or destructive interference, depending on exactly what the wavelength is. Okay, now the first order maxima is the first bright spot to the side of the central maximum. And so that occurs when the value of m is either plus or minus 1. And so let's just use plus 1, and the situation is symmetric. So if it was minus 1, it would just be the same situation, same values, except for on the negative side as opposed to on the positive side for y. All right, so we have the condition for first order maximum is that the path difference, d times the sine of the angle, is equal to exactly one wavelength. That's what first order maxima means. This is one wavelength. All right, so we need to figure out what the angle is for that. And so solving this equation for the angle, we get the inverse sine of wavelength over d. You plug in those numbers, making sure that the units are the same, so I converted both to meters, and we get an answer of 0.00158 radians. Okay, so the first bright spot beside the central maximum will be 0.00158 radians away. All right, now we can plug that into the tangent formula. Tangent of that angle is going to be y1, like how far away it is along the screen, divided by the length. And we can plug in their numbers and solve for y1 and find that it should be 3 millimeters away. So if our light comes in and hits these two double slits, or this double slit, Then there'll be a big bright spot in the center, and there'll be two bright spots to either side of it that are 3 millimeters away. One 3 millimeters above and one 3 millimeters below.